I need to correct a big mistake I actually found, and I'll reload the notes that I have. But those last two terms on the viscous sides, I'm really sorry about this. I have this term, and then for some reason, I have this. I don't know why I wrote that. It should be, obviously, it should be a delta squared. I just saw this when I was looking over the last thing I wrote, and I was like, that's not right at all, actually. So it should be a delta squared in there, and I'll reload the notes to fix this. But after the same processes, and again, you use this fact that you have to use this thing, you'll get that there should be no Reynolds number on that side. I don't know why I went all that trouble, but it's because before in the notes I for some reason wrote that, but it has to be squared. Same reasonings, but you'll get now this term on here, and that cancels out, so there's no coefficient in front there. I'll reload the notes. I hope you didn't focus too much on them. But that being said, well, we want now. This is the main assumption of boundary layer theory to get at that point. Boundary layer theory has the assumption that the square root of the Reynolds number is much, much bigger than 1. That being said, that kills this term, and that one hangs around. If both of them were that much bigger, they'd both drop out. So with that, after that being said, you then derive the boundary layer equations. This is all non-dimensional. I'll drop stars. Continuity. So this is momentum, continuity, and then we have boundary conditions. Where this is no slip, and then we have sort of mathematically the limit as y star. Non-dimensional y, remember, is y divided by the boundary layer. So the limit as y approaches 1, as y star approaches 1, that means that y approaches the boundary layer height, right? That means that's this idea that the x direction velocity has to approach the far field. So these are the boundary layer equations. They are sort of like the baby cousins of Navier-Stokes because they govern a lot. They're still a very rich, complex system of equations. But we got this assumption, and the Reynolds number thing came about to give us this. Again, these are all true. This is true. So those are the boundary layer equations. I will reload those notes. Please, please, please don't please delete the files that you have right now. I'm sorry I did that. But I will fix that error. So again, yes, there's a whole error where I left 2 Reynolds numbers around. I don't know why I did that. I was just probably rushing to make these notes. But so let's see, I have little red things on there right now. So I'll reload them. Please delete and forget everything about before. But yeah, you're supposed to get here. And this is all non-dimensional. These equations. So they should have all stars on them. That is the fundamental theory now of the boundary layer equation, right? The boundary layer that's happening on any surface sitting in external flow is governed by these equations. So they're actually simpler than Navier-Stokes equations to a fair amount. And now I'll give you a little rundown. So those are the equations. Notice, right, that we didn't know. We're trying to find right? We're given that set of equations. What we're trying to find out is the x velocity field and the y velocity field. So remember from a long, long time ago, in lecture 1, remember, right, what did we do to find those things? That was the whole point of a stream function, right? That was this psi potential function, right? That was a potential function that had those relationships of taking derivatives to get your velocities. So we don't have to do it now, but you should appreciate the fact that once we got to that simplified version of Navier-Stokes, then we pose a stream function problem. And this is what Blasius did, like a long, long time ago. Pose it as a stream function, derive an ODE for the stream function with the similarity variable, and then you get the Blasius solution for the boundary layer. But I think you can just appreciate that just from lecture 1, this whole idea of you have a complex set of equations, differential equations that need to be solved for two fields. You can make that simpler if you just search for the potential function, the stream function, and then do math on that thing. So that's how we got the exact solutions that you're getting in this section. But I think you all have the tools to understand how they got these solutions, and it's just what we did in thing 1 on the stream function. Search for the stream function. Don't search for the u, x, and y, v, x, and y. That being said, here's the highlights. So for the thin flat plate, governed by this situation, right? Obviously, the boundary layer height will change as we move along the plate. Okay. Here's the inviscid flow, so that this point has to equal the far field. Okay. And then here's some L for the plate. So the solutions are actually in terms of x's and y's, and we came up with sort of the greatest hits, or the highlights. Keep in mind this is Reynolds number with respect to x, and this is an x. So right here, x is equal to 0. Something happens weird. So here is an x naught, let's say. So this is for any length of plate. This is true. And then something else. We have this quantity, the momentum thickness, has another relationship. I'll just write in the 1/2. This momentum thickness is this relationship. And wouldn't you believe it, you also get the drag coefficient from this analysis. Skin friction. L, where this is the length of the plate. So keep in mind, if you see this is a pointwise Reynolds, this is rho, this, right, it's x, so it could be x naught, right, it could be this x naught, this can get x1, so as x increases, this Reynolds number is actually increasing because the length scale is increasing. So this is pointwise. The coefficient of drag is actually in terms of the length of the plate, not a pointwise. So if it's a finite length, this Reynolds number has an L, not an X. It's important to see that L. This is an L. This is a variable X. So it will change. So these are the main results, sort of solving those boundary layer equations that Blasius did and get a stream function technique to do it. These quantities I'll go into. You don't know what they are yet, but that's where we're going to go. This is that gosh darn skin friction coefficient that we were looking for, just motivated by example, the experiments of what is my drag force. See, it's a function of Reynolds, right? It amazes me how much stuff you can get for an engineering problem by just calculating a Reynolds number. And it shows up from this very rigorous approach to solve this flat plate problem. It's so complex, I'm not even allowed to do the stream function stuff for you to show where it comes from in this class. as opposed to internal flow. I could do some integration and some arguments with like shears to give you like the derivation of u of r, but I can't even actually give you the u of y for external flow just because it involves a lot of trickier things. But these are the important things, and these are like, they call these exact, and you'll see why they're exact, and you can have approximates, and the approximate being that you are assuming what the velocity profile is a priori. So this is exact meaning this is exact being this is for the true u of y. Right? This is a solution for the actual velocity profile. There are approximate versions of this where this is just some constant. So let's say C naught. And your book has these. This is like C1, C2. It's still the same dependence on the Reynolds number, but for approximate, these numbers change. And the approximations are coming from, you're just assuming what this velocity profile is before you do any of the stuff. So it's kind of cheating, but you can do this usually because I know it's curvy, I know it goes to 0 and has to go to a value. You just need to pick some function that will do that, and you can get results that way. They're not even that far off. So your book has a table that describes what all these different constants are. Please use the exact or the Blasius constants with the 5 and the ones I wrote down before. That way we're all on the same page. That being said, I encourage you for any of these problems that you have in homework or etc., just be very explicit about which of these constants you're using, and I'll make sure you won't get docked points. If you say according to a parabolic velocity profile and use the right constants, I can't tell you you're wrong because you're using the right constants. But I prefer if everyone just use the exact Blasius constants. So next, we're going to describe what these two variables are and what you'll use them for. Right. So next, you already know what the coefficient of friction is. Helps you calculate drag forces. These ones are right. This is called a displacement thickness. This is called a momentum thickness. So I'm going to go over what those two things are, and they help you reason some things out. They're pretty equivalent, right? As of now, you've done enough, right? These are kind of the analogies to like that V-bar and that equivalent length. Right? For pipes, we just wrote these. We wrote some variables out there. We're like, what's a good like abstract way to think about this in terms of just scalar multiplication? We had an average velocity, and we had this equivalent length for those friction factors. The same stuff, more complex, but same idea.